Dr. Alizan in the chat if you want to have a look at it.
Okay, let me see Chat.
Okay.
Okay. Oh, there's quite good conversation here going on in the chat. I can see the slide. It's 5 now. Have a longer break for Asa. Okay. This just to incentivize participation from you. I will award 1% total mark for those who ask questions. Oh, that's very good. 1%. That's represented. Open the floor. You should grab this opportunity to ask questions. Yes, yes. Please try to ask questions as the slides are being presented, so that you get the maximum result out of every slide. I want you to have a KPI for every slide for yourself. That means as I show one slide, try to get the maximum that you can out of that slide. Try to understand that slide. Whatever your background is, don't be shy, don't be afraid to ask questions. Try to get the maximum that you can out of that slide. If you cannot understand the slide, say which part that you cannot understand so that I can do more explanation. For ML in healthcare, what is the best framework platform to use? TensorFlow or others? This is our area. I think Dr. Izam also can elaborate on that. We have done some work on healthcare, particularly in epidemic management, just like what we have right now, COVID. So we've already done that for tuberculosis, and we already done that for typhoid. There is no clear answer. What is the best program to use? Which is the best framework to use? All these frameworks are generally general frameworks. It depends on what you actually want to do. Later we will go through some detailed slides. Possibly you get a better understanding of what I mean by that as we go through our detailed slides. I think this Sina mentioned this very good. Best is quite subjective and can be a matter of dispute. Correct. TensorFlow is definitely one of the most common. Yes. TensorFlow is quite one of the most common AI that is being used. It's based on Google's AlphaGo platform, which is a general use platform which shows its capability to defeat the best Go player in the world has been defeated using AlphaGo, and they are using it for other purpose right now. So one of the derivative of AlphaGo that you see now is TensorFlow, for example. It's one of the best that you can start with. The pre-processing just algorithm and tuning is what matters. Correct. Sina is, which of you is Sina? That's Sina, is it? Where are you from, Sina?
I'm from Iran.
That's very good. Do you have a lot of Iranians here in this group, or just you alone?
It looks like I'm alone.
Okay, very good. How long have you been here in Malaysia?
It's now I think 10 or 11 months.
Okay, you're just here recently, right?
Yeah, correct.
We also had an Iranian. I have two friends from Iran. One is Brandon. He lives somewhere near my house. And another one is Brandon Lanza. That's his name. Brandon Mehdi Lanza. And another one, I forgot her name. She's one of the staff in our company some time back. Definitely the proof can give better answer. Yeah, the professor, okay. Could we use the hybrid algorithm such as clustering and classifier to increase the accuracy? That depends on your problem. Later I'll go into the types of AI that you can use. So classification problem is where you use that's situation where you use classifier. There's situation also where you use clustering. There's also situation where you don't use classifier, you don't use clustering, for example, and you use other forms of learning. Whether or not hybrid algorithm will be useful depends on your situation. There's no hard and fast answer to any particular problem. Yes, maybe element of data set that we have to look at is important part. Yeah, also objective. Yes, this is correct. Hashima. Which one is Hashima?
Yes, it's me. That give the $1 million questions.
Yeah, okay, that's true. Data, like I mentioned in one of the slides just now, that it also depends on the quality of your data. Okay, what kind of just now what I mentioned was what is the granularity of your data, whether you have a lot of missing data in your data set, how accurate is your data, whether your data got any false data inside. Obviously, for example, if you were to take a data from, let's say, a waste, for example, data from waste is almost 100% accurate, because why? Because the person actually traveled to that place. You know, you cannot get his traveling unless he travel. But if you ask data, let's say for example, data from Facebook, you don't know whether the data is correct or not, because some of the things can be you know, people pretend to be somebody else and this kind of stuff. Then yes, the same question about hybrid algorithm. Could we have RL, Q learning, deep learning, and if this combination? So there's no fixed answer to this kind of question. It depends on what you want to do, and what you want to and the data that you have, and the algorithm that you use. So there's no one answer fit every situation, kind of issue, right? Okay, I'll go back to my screen. Yes, yes.
I have one question.
Correct. Okay.
Is it okay for me to ask a question?
Yes,
now?
yes.
Okay. First of all, I'd like to introduce myself. My name is Mazhar. Actually, I've met you in a couple of sessions before. If I'm not sure if you remember me, I'm Fendi Friends, the one from the Ministry of Agriculture.
Yes, Mazhar. Yes. We met before. Yeah. Good.
I happen to have one question. From your experience, when we run a training data, and let's say we have not a very good result, is it because of the lack of training data, or how to determine which one to choose? Either we have to increase the training data, or we have to choose a different kind of algorithm for that specific task.
Okay.
From your experience.
Okay, good question. Good question. From my experience, we have to first of all ensure that we plug the low hanging fruit first. Okay. So let's say for example we need to generate some cash lah from our katakan pokok plum, for example. So what we do is we make sure that we get all the low hanging fruit first before we go for the higher hanging fruit. Higher hanging fruit means they are more expensive lah for us to go and get, kan. So if you can find the low hanging fruit, you handle the low hanging fruit first, because you want to generate the cash without spending too much money. And then once you have money, then you can spend more money on looking for the higher hanging fruit. So what does that mean? That means it depends on your situation. If we look at your situation and then we see your data is not enough. Not enough in terms of quality, diversity, or not enough in terms of quantity alone. You may katakan for example you're taking padi punya data, paddy, rice field, and you want to analyze that rice field for, let's say your mission is to increase yield in Mada, for example. Mada is the biggest rice field in Malaysia, is in Mada, which is in Kedah. For Malaysians, for non-Malaysians, you need to know that Kedah, which is in the north peninsula of Malaysia, used at one point of time be known as the rice bowl of Malaysia, because they are where we plant paddy. And then there's a small area in Skinchan, which is in Selangor here, near Kuala Selangor. This is the one with the highest yield of rice. And then there's another area which is in Kelantan, for example, which is also fairly big, but also low yield. So maybe you want to fly drones, Macam Mazhar, that's what you're doing. You want to fly drones, and then you want to analyze the color of the leaf or something like that to see whether we are reaching down to into the ground sufficiently enough and all that. By the way, Mazhar, are you doing masters now or PhD?
Masters.
Okay, good. So I think you're also fairly familiar with TensorFlow semua, kan?
Yes.
So when you are doing that, when we look at the situation, first of all we see that we look for low hanging fruit lah, across the board. We look for low hanging fruit. Number one, we look at data first, whether your data ni not enough diversity or not enough quantity ke apa ke. So maybe we can solve that problem, but not 100% solve. We can solve 60% of the problem. But 60% is cheap to solve. Then another 40% is expensive to solve. So we try to solve the 60% first. Don't solve the 40% yet because it's expensive. Quite importantly, you must make sure that you are using the right algorithm, okay? So let's say, for example, you use the algorithm or the parameters to the algorithm or the architecture of the AI, and then you find that you have some reason to doubt though that your algorithm is correct. That is something that you have to fix upfront, because you cannot keep on training the wrong engine to do the right thing. You are wasting your time, you are wasting your data, you are wasting your resources, your time apa semua, trying to teach, let's say for example, you're trying to teach a fish to climb a tree, for example. So you know a fish cannot climb a tree, you must teach a monkey to climb a tree. So if you find yourself dealing with a fish, you definitely have to move on to something else. So if you try whatever you can pun with the limited data that you have, and then you find that it's not learning at all, ataupun your learning rate is too low, then you really have to inspect again lah your architecture or your algorithm ke apa ke. Maybe that's not something that you should do, but you should be doing something else lah. You be mindful of that lah. You don't teach a fish to climb a tree. You have to find a monkey to climb a tree. So you find a fish that is something like a monkey pun tak apa. Rather than, you know, if you want to get a monkey, it's too expensive, we can find a fish that is something like a monkey pun is okay juga lah, you know. Again, it's back to what Hashima said just now. It's back to your objective. If you can achieve your objective and at a lower cost, given the resources that you have, then by all means try to do that lah. So maybe you don't reach 100% of your objective, but you reach only 75%. But nobody else is 75%. Other people is only 30%. Pun dah good enough dah, you know. Then with that you can generate some money, and then after that you can move on to something else lah. Okay.
Okay, thank you very much.
Most welcome.
Thank you very much.
So it's back to practicality lah basically. Come back to how practical it is to do things. Any other questions? Tak ada. So I'll move on to the slides back again, yeah. Okay, we are going now onto the type of machine learning. Just remember, just now we're talking about what is AI, what is machine learning, what is all the rest of the stuff. So what are the type of machine learning that you have? So once you have this slide, you can have a look at this diagram on the upper left hand corner here. There are a lot of types of machine learning. Okay, what we were talking about just now is classification. So the graph at the bottom here on the right, this shows a classification problem, where, for example, you want to identify, katakan, sick paddy from healthy paddy. You want to fly a drone. The drone flies on top of the paddy field, and then it takes color of the leaf of the paddy field, and analyze the color of the paddy field, and then determine whether the paddy over there is suffering from some kind of disease, or the paddy is healthy. So you want to divide what is healthy paddy against what is unhealthy paddy. So normally in machine learning, what you do is you take whatever data that you have and you convert that data into numbers. Okay. For example, when you fly a drone over the paddy field, you're getting, for example, dia punya color, and the color is a number, color of the leaf. And then based on the color, you train the data. You train the neural network using data that you have to differentiate paddy of what color is healthy, paddy of what color is not healthy. And then you can draw a line in between them to differentiate between paddy field and healthy and non-healthy. So in order to do this, in classification training, you go through what is called supervised learning. So you can see here in the tree diagram over here, the org chart, you have machine learning on top, and then you have supervised learning. So what you do with supervised learning is you have feature and you have label. Feature is the number that you generate from the data. For example, there could be number for the color of the paddy. That is a feature. And then label. Label is the result that you want. This paddy is healthy, the category healthy. Or this paddy is category unhealthy. Or it can go further beyond that. This paddy is not healthy, subcategory dia not healthy because not enough water. On the other part is category dia not healthy because too much water. Or the other one is not healthy because of certain disease or certain pests, for example, tikus or something like that. And then or the brown, whatever they call it, this brown plague or something like that, the kind of insect that attack the paddy leaf. And then so not healthy pun you can have subcategory, subcategory like that. So these are all categorization. So what you do with categorization is you capture the feature, you capture the data, and then somebody go and you take some data for training purpose. For training purpose, for testing purpose, you take some data out, and then you manually go and classify this test data. You say this color yellow means what? Color orange means what? Color brown means what? Color green means what? You personally do, and then you run the training on the train data, and then you let the machine do mistakes. The machine will say green means unhealthy, and then after the machine has gone through all the categorization, and then you compare the result with your actual answer, and then from there the machine learn that this one is wrong, this one is right, and the machine goes back and correct itself, then it goes through a second round, third round. So that is classification under supervised learning. There is also something under supervised learning which does not involve categorization. For example, katakan back to the paddy just now. Paddy ni they use a type of chemical fertilizer called NPK, nitrogen, phosphate, and calcium. So there's a mixture in NPK, maybe 50% nitrogen, 20% calcium, phosphate the remaining, ataupun maybe nitrogen is 80%, then the rest is 10 or so looking at the color of the leaf, how much N punya percentage, how much P percentage, how much K percentage must you apply to that particular type of color in the leaf. So this is not categorization, because this one is how many percent. How many percent is a number. It's a number, not a categorization. So you do regression. Regression is the graph on the left. Okay, you plot your data, and then you try to draw a line that averages out to show the trend in the data. So that line will help you to extrapolate. Katakan now you know something is the value, but you don't have the data yet. So what is your prediction for that particular color of the leaf? How much N, how much P, how much K do you want to put? So you look at the graph you can have one graph for N, one graph for P, one graph for K, for example. So it's not a classification problem where it's not labeling the data, but it's trying to extrapolate what is the value of something. If the X is known, what is going to be the Y based on the average that you get from the data that you have previously. So those two are supervised learning. Now unsupervised learning is a bit different. Unsupervised learning is where you don't know how to even draw an average line, or you don't even know how to cluster the thing. Let's say for example just now that makeup just now. So let's say for example we totally don't know how to match cosmetic to face, for example. It's something that we don't know because it's not our domain knowledge. Tapi what we do is we let the machine run through the data and let the machine do the clustering itself. So the cluster may not have any name. For example, katakan you may have a cluster of fair skin plus wrinkle skin plus kata sagging eyebrow, sagging eye bag ke something like that, or hidung or nose is corner to the side or something like that. So what do you call this cluster? There is no label to name that cluster because it's a mixture of this plus this plus this. And then you may have a different cluster, katakan somebody with very fat cheeks kata, ataupun very thin cheeks ke, high cheekbone ke apa ke pula, that is another cluster pula lagi, plus white skin ke ataupun dark skin ke ataupun yellowish skin ke ataupun purple skin ke or spotted skin ke whatever. So you have another cluster. So we don't know how to cluster that one. So what we do is we let the machine run through something called unsupervised learning, so that the machine can now match the feature, which is the figures that is generated from the data, and then cluster the data according to certain cluster, so that we can address the cluster as if the cluster is the classification. So if people fall under this cluster, you go and recommend them this particular package of cosmetic. For people who go under a different cluster, you recommend them a different package of cosmetic. Now, the biggest part of machine learning itself is what you call reinforcement learning. I will show you an example of reinforcement learning shortly. Reinforcement learning is where we don't label, we don't cluster. What we do is we give a reward to the machine. This is sama macam, is the same as you are trying to teach, for example, an elephant to perform in a circus. Okay? So we don't teach the elephant, but the elephant will try to do all kind of thing, and then when the elephant is doing the right thing, we give the elephant some food. If the elephant is doing the wrong thing, then either we don't give food ataupun we punish the elephant a bit with a negative point. Maybe whatever lah, you know. So then the machine learn, if I do this, I will be rewarded. If I don't do this, I will be punished. Slowly the machine will learn, you know, what I want to do or what I don't want to do. For example, for a car, let's say for example you do the remote control car lah, but your remote control car is managed by AI. It's not managed by a remote control, but AI is running the car. So you don't have to teach the car anything. The car will go by itself. But if the car collide, for example, hit another car, then the car will be slow, kan? If the car hit the side wall ke, atau fall into a dish ke, fall into a drain ke, then the car will be slow. So the reward here is for the car to be number 1, number 2, number 3, or number whatever, top 10 ke, so you have some reward. So the car will learn though, if I reach top 10, I'm going to be rewarded. Slowly lah. It takes a long time, but the car will slowly learn. If I am fast and I get a top position, I will be rewarded. So this is what I must do. I must not hit another car. I must whatever you must do lah. Go fast, don't go slow. Cornering must be nice. Take a tight corner. Don't hit the wall. Don't fall into a drain. Don't fall into a dish. So the car will slowly learn in order to win the reward. So a lot of machine learning that we are looking at now is called reinforcement learning, where we design the reward. So you must also design the right reward for the machine to learn. Let's say for example you design the reward in the wrong way. So the machine will learn the wrong thing because it's chasing after a different thing. It's just supposed to chase after this, but it's chasing after that. Say for example lah, you are running katakan some method of selling insurance, okay, using AI. So you have data about your target market. You have data about personal data. You get some data from somewhere. You get some personal data apa semua, and then you do some packaging of insurance product, and then your reward is to get more customer. Okay, is that the right reward tak? More customer, or you want to get more profitable customer? So you don't have so many customer, but you are targeting for profitable customer as opposed to unprofitable customer. Unprofitable customer tu, for example, that fella is already a sick guy. He need to go to hospital every often, and then within 3 years he's quite likely going to die. Okay, you can get a lot of this customer. So if you reward in terms of getting a lot of customer, you may be getting a lot of customer but the wrong customer. So in the end, the more customer you have, the more is your cost, because you have to pay the insurance to them. So maybe your reward should be not more customer but more quality customer. So it's not more customer but it's more quality customer, like that. Okay, so these are the types of machine learning that I showed just now. Supervised classification is where you have features. Features are the independent variable that influence the factor that influence the result that you want to get. For example, what is the height and the weight and the age of the people that you want to insure. And then label, for example, based on the height, weight and age, you can determine what is the gender of the person. Let's say you don't have data about the gender of the person, but you have data about height, weight and age, so you have a fairly good way of estimating gender based on height, weight, age. That is the hypothesis here lah. Whether the hypothesis is correct or not, that's also another question you have to ask. So one of the supervised classification learning that you can do is, given a person's height, weight and age, try to predict his gender. So your result will be a percentage. Your result is not like, oh, this fellow is a male, this fellow is female. Maybe your result is, this fellow is 60% maybe a male, 40% maybe a female. You know, that kind of answer. This is where your fuzzy can come in lah. And then when you have also supervised learning, which is regression. For example, what is the size of the house and what is the number of room in the house? You notice, we are converting the factor back into number though. So your house is what size? How many square foot, built up area, and what is the number of rooms? So these are all quantitative factor. And then from there, you don't have label, but you try to determine what is the price of the house based on the size and number of room. So it's again a number. So given a house size and number of room, try to predict what is the market price of the house. Now, in unsupervised learning, where you do clustering, where you allow the machine to do its own clustering, you have, for example, independent like company, for example, what is the annual turnover of the company? What is the total asset of the company? Now, how many years have the company been in operation? So there are no labels. We don't have to label it, but the machine will cluster the company according to that annual turnover, total asset, and years in operation, and try to predict. If you give a new company to the machine will try to predict this company fall under which cluster. But the machine don't know what is the meaning of this cluster. Then the data scientist and the data analyst will have to come in and look at the clusters generated by the machine and give it a label. For example, the company can say, the analyst can say, this cluster is called new company that has a poor chance of survival. Another cluster will have new company that has a very good chance of survival. Another cluster will have new company that has a very good chance of flying high. Another cluster may be old company that has no chance of survival. So you look at the cluster, and then the human must provide the contextual interpretation to the meaning of that cluster. Okay. So these are the types of machine learning. There are many more types. These are not just the only types. There are many more types. Okay. So what is artificial neural network? So if I appreciate that some of you have not even know what this is. So artificial network looks like this. It's like a neural. It's supposed to resemble a neural network in a person's brain. Later we go into more detail what are all this means. But basically it means that this whether it's a square or whether it's a circle or whether it's a rectangle, and then you have lines from this rectangle, it goes to another rectangle. This line is called the network. So you can see that it's all network, and then these are all the neurons. So the neuron is inside a network. That's why it's called a neural network. Okay, let's see how we are training a machine. Just now we saw this. This last one is reinforcement learning. So that's this. We are going to look into that. So what the machine does is that there are three factors in the reinforcement learning. One is the environment. The other one is the agent. The agent is the machine. And then the action that the agent does within the environment that allow it to earn rewards. So the cycle of action that it does is, first it does something, and then it will that does something will produce the result, and then that result will be evaluated in terms of whether it's earning enough reward or not enough reward, and then the machine will think of how it should adapt whatever it's doing in order to earn more reward, and then it will do again, and then check the result again, and then evaluate again, and then adapt again. So that is this is an example reinforcement learning. This guy has linked up his AI to his computer to learn how to play this thing lah, this game Mario Brothers. I don't think you can hear the sound, but I just jump and I just describe to you this. We are not going to watch this whole thing, so we just see how it is. So here is where you see the person has already trained the machine. The machine already know what to do, already know whether to press the up button, down button, left button go stand or slow down, the right button to move ahead, or maybe the space bar to jump. So the machine already learned. So you can see that the machine is now playing like a master player. But how did this machine start learning? This is how the machine start learning. First of all, you can see that the neuron, okay, here is a picture of the neuron at the top of the screen. At this point of time, the neuron is not so rich yet. So that means they have not yet gathered enough data. So the machine has not yet learned enough from doing things. So the experimentation is not enough. So experimentation is not enough. So you can see now the machine has stopped. So the machine is stuck over there. By pressing the wrong arrow apa semua, the machine has got itself stuck. So it's not moving. Then they restart the experiment and train again. So they took something like 30 to 50,000 iteration to teach this machine. And macam AlphaGo tu, what they did was they did two machine to fight each other in the game of Go. Millions of time in order to teach the machine in order to fight a human being. So this is the process is where they are building up the neural network. So as they build up, the machine starts to learn and become fitter. So this is in terms of the reward that the machine is learning. So you can see as the thing move, you can see the neural network become richer. There are more lines there. So neural network is now attaching certain symbols that is able to detect on the screen to the action it's supposed to do. Press A key, press B key, press XY key, Y. Apa semua tu do. A is move left, B is something lah, move right or jump or something like that. So, so as the machine build up its neural network, the machine is learning. Just like us. Kalau we train our brain, we study more or we do something more, our brain will have more dendrites to each other. The neurons, there will be more neurons in our brain connected to each other. So neuron is not something that we can grow very fast. There are some people say they call brain food apa semua, you can have to grow your neuron. But neuron is something more or less fixed that we have. What we can add or remove is the connection between neuron in our brain. Likewise here in our machine, the more connection that we have between our neuron, the smarter the machine becomes. So you can see as the machine has more neurons, it has become smarter and smarter. So now you can see that this guy already knows where to jump and all that. Compared to earlier on, where the neuron is not so rich, he doesn't know what to do. He just keep on running like that only. That's all. Get stuck, get shot. You get shot. So this is how you basically train a machine lah. Okay, let's move on to the next one. Okay, this is our break time. Any question that we have so far about this artificial neural network? I'll go back to the earlier slide. Type of machine learning. Okay, what we have learned here before the previous break until now is what type of machine learning are there, and then then from here we focus on reinforcement learning, and these are again a recap of the types. And here we look at an example of reinforcement learning. So any questions so far?
So supervised learning, unsupervised learning, those things were very clear.
Yes.
Coming to the artificial neural networks.
No, supervised learning and unsupervised learning is also using artificial neural network. The whole thing that you saw just now is using artificial neural network. Whereas
the understanding of supervised learning and unsupervised learning was clear right now. Coming to the artificial neural networks, if you can elaborate a bit, it will be helpful, sir, about the neurons, what happened there.
This one we have later slide. After the break, we will go into detail.
Okay, sir. Okay.
Any more question?
I have a question. Actually, I asked you for an opinion.
Yes.
For this current situation, artificial neural network, let's say Alexa or the latest one is Inception, ResNet, B2 or AI, not sure. They're already going up to 1 million of parameters.
Yes.
And for today's computing processing, we are already actually closer to a limit where the transistor are now at the size of an atom. That is 3 nano meter.
Correct. Even Huawei is coming out with all these nano punya kind of
Yes.
correct. Yes.
So, in order to improve this artificial neural network, what I read is that they are increasing the parameters. Now, Google is coming out with a new algorithm called GPT-3, which have 1.75 billion parameter, and the performance is already closer to human level performance, where humans 80% in doing text, in arranging text for speaking, and the GPT-3 is already 79%, I think. It is almost as accurate as human.
In terms of text
but
generation,
now-
yes, correct.
Yes, but now it seems that like the processing is seems to be the problem, because we cannot make the transistor to become more and more smaller, because it already reaches
Size of the atom, the limit.
size of an atom. So, in your opinion, what is the future of this artificial neural network? Will it be expanding, or will be limited and come to the second winter of artificial neural network because of the processing power?
Yes, that's why the companies are all what you say is true. We have already approaching the limit. So in terms of transistors, we are approaching the limit. So now the problem is to replace the transistor. That is why now people are working on quantum computers lah. For example, which use a different kind of mechanism altogether to represent the data. Ataupun we are moving towards biological computers, which uses protein atoms instead of transistors to do. So within that box, too, we are already full. So now what we need to do, we need to move to a new box. Sama juga like Earth, for example. Earth is like so problematic. That's why Elon Musk wants to go to Mars. USA wants to go to Mars. China also wants to go to Mars, but starting with the moon first. So we have to we cannot do anything lah. The box is already like that. It's already the size of the atom, and we have no choice about the size of the atom. So we have to move on to something new. So something new is where we can tweak the larger parameter pula. Instead of that one, we cannot do anything more. If we just go on with our current technology, we will definitely hit a limit with what we can do. Because we must remember, the human brain is more powerful than the neural network in some way lah. In some way, it's more powerful. But the human brain is not a digital punya machine though. It's an analog machine. The human brain is using chemical and electric, for example. Electric pulsar as well as chemical, and the chemical of the human brain is very complex, molecular punya kind of science. So that is why the human brain does not have this kind of capacity punya problem, because the processing itself, the underlying technology behind the process is a natural punya technology, uses protein and all that, which is much more complex than it. One interesting area you can look at is how mushroom, what you see, what we eat normally mushroom, that is only the sexual organ of the tree, the plant. Actually, mushroom is not a plant lah. Mushroom is called a fungi. Fungi is a kingdom by itself. So there's a fungi kingdom. Then there's also a plant kingdom. Plant kingdom ni all the normal trees that we have. And then we also have the animal kingdom. But the fungi kingdom is not a plant, it's not an animal, it's a fungi. So mushroom is a fungi. So the mushroom, actually the body of the mushroom is underground. This is called the mycelium. The mycelium network tu is very big. The biggest fungi, the biggest organism in the world is a fungi in US. I think the size is 3,000 acre or something like that. That's one single organism though, 3,000 acre size. So it's all underground. So mycelium is the root of the mushroom. It looks like a root. So the mycelium network ni connect tree to tree though. The mycelium network must go into a tree, and then it goes into another tree, and then it carry information from that tree to that tree. For example, if you put certain kind of thread to the first tree, the second tree, maybe 1 kilometer away, will start to produce some kind of chemical that will prevent the threat from coming. For example, kata there's a type of ant or aphid that will attack the leaf of tomato plant. So if you put the aphid on the tomato plant, And then underground there are some mycelium going from that tomato plant to another tomato plant, maybe 1 kilometer away. So the plant that is attacked by aphid will produce certain kind of chemical that is poisonous to the aphid. So there is no second attack. But the plant, the 1 kilometer away, also start to produce already that chemical so that the aphid cannot go there. So it's using the mycelium network to communicate. But what is the mechanism of communication? The mechanism of communication are the nucleus inside the cell of the mushroom. And so happen that the cell of the mushroom does not have one nucleus. Like we, human or plants have one nucleus every cell. So in a mushroom, every cell have multiple nucleus. And the cell is like, one cell can be like 1 kilometer long. So the cell from that plant is one single cell traveling to another plant. And then the nucleus will move from there to here, carrying the information. In the form of what? In the form of chemical punya information. So that chemical goes there and that is the information decoded by the plant to do something. So coming back to your question, so we are now processing data using electronics, and then we are digital, and then using transistors in order to keep the bits and bytes lah apa semua. So we cannot go beyond the size of the atom itself. Unless we can start to use electrons to represent, ataupun we can start to use proton, then we have multiple electrons. But we have to change the game lah basically. We have to change the boundaries of the game, we have to change the game. This is the moving forward. Kalau tidak, your answer is correct. That we will reach a limit. Also the other question is whether we need to reach the limit lah. That's another one. So maybe in certain applications like military ataupun socio-economic impact study ke, you need to have so many parameters. But do you need to have that many parameters for something else? And how useful is that thing? For example, tax arrangement. Maybe tax arrangement is not that critical for survival of human race. But then it's being used to train the thing so that we understand how to manage a machine learning that has thousands of millions of parameters. There will also be some techniques that is involved in there for us to be able to make that process more efficient and stuff like that. But the result right now, the tax arrangement tu, the ability of the machine to produce kata Shakespeare kind of work ataupun Stephen King's kind of work, is not really that important to the survival of the human race. But the technique to produce that can be something that can be applied to another situation that is important to the survival of human race. So we also have to, again, we have to prioritize where do we need this and where we don't need this. But in order to push the envelope, definitely we have to look at new techniques like quantum computing or using protein as a way of calculation or whatever lah. Right?
Thank you for the question. I have one more question.
Yes.
And because talking about the quantum computing, so recently the Jiuzhang quantum computer, which achieved the quantum supremacy of
China,
solving the Gaussian sampling,
yes,
and suppressed the Google quantum computer. But this quantum computing is different with this classical computing, where classical use the bit 0 and 1, where the quantum computer use quantum bits.
Qubit, yes.
Yes, qubit. It is simultaneously at both points 0 and 1 at the superposition.
Yes.
And also because of the language, all of the coding, the code is not different with the existing classical computer. It will become, it will take some time for us or for the computer people to get familiar or get along with the new kind of code.
Yes.
Code a new, in your opinion, and in your stand, is this quantum computer will be like the computer we're using today in quite few decades, or is it important for us to start now learning about the quantum computing?
The way I see it, the programming quantum computing ni, I see that computer will program the quantum computing. Another AI will program the quantum computing, not human. This will be a situation where I also cannot imagine how lah. I had a conversation about this situation. What if later on computers can produce themselves, and then where is the human needed anymore in this equation? Kan? Let's say for example human don't have to work anymore, everything is being done by computer. Then how do we reward humans Right now, salary, for example, is a reward scheme for humans. So that is how human can survive, individuals, because we have a scheme for paying people based on salary. Now, what if now human don't work anymore? How are we going to survive? How are you going to distribute the reward to humans and stuff like that? So are we going to fall back into a communist regime ke apa ke? Everybody has katakan a book of ticket. You need to buy, you go and take the ticket, and once you finish, that month is your book. Then you survive. You survive on the book that you allocate for that month. Next month you get another book or something like that. We don't know yet. These are all very new things that people have to think about lah. But in my stand, I foresee that the computer is too difficult for human to comprehend because of the superposition. It's very hard for us to imagine. Katakan for example, I ask you imagine a problem that is solved by a cube that is a hypercube that is 11 dimensions. So it's very hard for us to imagine a cube that has 11 dimensions. For us to be able to imagine a cube that has 5 dimensions pun is already so difficult. How can we imagine a cube that has 11 dimensions? So when we talk about superposition, it's much more difficult because the bit and the 0 and 1 can exist at the same time, as you say. So there's no truth anymore, which is a fairly good representation of reality. There is no absolute truth as far as creation is concerned, because some truths can be false once you bring it up to a different level. Like for example, Newtonian physics is false once you bring in Einstein, and Einstein becomes false once you bring in quantum physics. So at a certain level, we still use Newton, walaupun we know that it's false under us in a different level. So there is a usage for Newtonian physics. Most of the thing that we do on Earth right now can still apply Newtonian physics. Like you want to construct vehicle or buildings or whatever, you use Newtonian physics. But then you know that it's false under katakan Einstein ni, but then you have to go at the speed of light before that thing becomes false. So you don't have to worry about that. But still, at certain point, you have to start to get worried about it. And then even Einstein is wrong because Einstein is dealing with things at a very large scale, but at a very small scale, the quantum physics come into play. So Einstein is so wrong. So there's a situation where you can apply Einstein, but then there's only a certain situation where you need to apply quantum physics anymore. Einstein doesn't apply anymore. The Newtonian physics doesn't apply anymore. So it's a matter of prioritizing what you need and use what you have in order to do something. But when it comes to quantum computing, when we really need to use it, I believe that human brains have very high difficulty in being able to formulate solutions, strategize how to formulate solutions using quantum computers. So I think maybe this is not publicized, maybe this is being kept behind apa benda ke, but I think that that people are now trying to produce computers that can program other computers, and in particular in quantum computing, I think that we will have machines programming machines later on. And once we are able to program the quantum computers, there's no doubt about it that quantum computers can definitely program themselves. So how soon is that going to happen? I foresee that it's going to happen within 10 years basically, because things are moving so fast. The only provision is that, okay, maybe 10 years we can still survive, maybe we can still see some of these things come to fruition, but maybe after 10 years, I myself have some doubts whether or not human being can survive anymore in this world, given that all kind of problem that and you can see that people are being very serious about this moving to Mars. People are being very serious about it. It looks like it's a game or it's a hobby or something. It's definitely not a hobby, definitely not a game. People don't spend money like billions and trillions of money sending people somewhere. I think because people have already got that idea that human beings are not going to survive anymore on Earth, and then we need to establish a new colony somewhere else so that there will still be a human race in the universe beyond, let's say, 10 years from now. So the time frame I think is 10 years, quantum computing. And I think the answer to your question is computers will program quantum computing, and maybe quantum computing at one point will start programming themselves. How human will fit into the equation is a subject for debate basically.
Okay, thank you for the answer. Thank you.
Any other questions? Interesting questions that we are getting. That's very good. Let's have more questions.
Sir, can I know
when you train your model, right, after you evaluate, right, for industry, you need to deploy to the customer, right?
Correct.
Clients, right?
Yes.
So, if your machine learning model fails in some situations, then how are you going to explain your machine learning model, why it explains, why it fails in these situations? How are you going to explain? Yeah.
Normally you blame the customer lah. You say like your data is not good or whatever. But the truth is that if you are really looking for the right solution, you must not fail lah basically. To manage a machine learning project is not the same as managing a normal project, you know. You cannot have the normal template for software development, then you apply that template to machine learning. It doesn't work that way. Machine learning involves a lot of experimentation. And the methodology for training a machine is still a very vague area lah. There is no solid methodology for training machine. But if once you graduate and you come out, right, I'm also involved in some of these projects. I see that project managers have no understanding in the first place that you cannot manage machine learning the way you manage software development. And because they are project manager, project director, you know, it's very hard to change them because they think they're already so high up, they're so big, or they're so grand or whatever. So you are fresh people, you're coming out into the world. You sooner or later you'll be managing vendor, for example. There will be vendors who produce machine learning solutions for people. Or you might be a project manager, you'll be managing your delivery team. You must understand that machine learning is all about experimentation, but it must be a targeted experimentation where you will fail. The thing about machine learning is that you will fail. This is how the machine learn. The machine learn by failing. So you will fail, and then from that failure, you must direct the machine in order to learn in the right direction. Let's say, for example, that question just now. You have to make sure that your machine is learning the right algorithm. Okay. So no point you try to improve your data when your machine is a fish and you want the fish to climb a tree. No matter what you do, the fish cannot climb a tree. So you need to find a monkey to climb a tree. So you must steer your team in order to develop a monkey because you want to climb a tree, not develop a fish and try to develop a fish to climb a monkey because the algorithm is wrong, architecture is wrong, the approach is wrong, or the parameters are wrong, whatever lah. So it need to be a directed experimentation exercise. So what is a good directed experimentation exercise and what is a bad directed experimentation exercise? This involves a lot of judgment in grey areas. So in order to answer your question, so number one is you cannot use the normal. If let's say for example your machine cannot be trained, and then you want to send it to the customer already, it cannot reach that stage. You know, you must know during your development process itself that you are having a problem. And then you must already identify what is the problem, whether your choice of architecture is wrong, or whether your algorithm is wrong, or whether your approach is wrong. You must already identify while you are doing the experimentation. And you must, if you need more time, you must already tell your client that we need more time. Or maybe their data is not right, or their data is not relevant. I see project where the client come in with data that is not relevant, but people don't measure the relevance of that data for what they want to do. For example, let's say for example you run a clubhouse and then you have some parameter about your members in your database, and then you want to know whether because when the member comes to the clubhouse, you can extend credit to the member. The member can buy drinks, the member can use facility, and then they don't have to pay until the end of the month. Some member go and gasak like there's no credit limit. So you want to play around with the credit limit so that you can entice members to come to the club and use more facility. At the end of the month, you can charge more because they use more. But then you must also make sure that the member can afford to pay. So you need to have some transaction data, not only your profile data. So some people say, oh, profile data is good enough for us to predict whether this member is good or not good paymaster. But then the profile data could be 5 years old or 10 years old. Maybe that time the member just came in and registered 10 years ago. So you're using 10 years data in order to predict whether he is now a good paymaster or not. Whereas you could check on the transaction data, like how they pay their monthly bills, or how much they purchase, or maybe they pay 2 times, or maybe they pay 3 times, or where they pay everything, or they pay prepay or something like that. So I see vendors coming in that situation, but because they want to get the job, they say, yeah, they are willing to do it. The data is fine. Then suddenly in the middle, somehow they have to own up, or they have to confess that the data actually is not enough. So you have to address this kind of problem while you are doing the project. Not today you have to deliver, today only you start to tell the customer, oh, actually our model is not working. Of course, that one is looking for disaster lah, basically. And of course, this one also is where you need to produce some measurable KPI to manage your vendors. Or if you are a vendor, you have to agree to your customer on some measurable KPI. For example, let's say if last time without machine learning, you have to charge 50 cents per advertisement, because advertisement is not targeted. So you may be publishing a lot of advertisement, but then you are not getting result. But let's say, for example, with machine learning, now you can charge 5 ringgit per advertisement. But then that advertisement is supposed to generate a lot of result. Let's say, for example, you're selling insurance product. So your insurance product, you can blast your insurance product to the wide range of people. But then these people, mostly they will not buy the insurance. Or insurance product, you can charge even 5 ringgit per advertisement, because if you get one customer, maybe that customer can bring to you income of, let's say, 500 ringgit. So 5 ringgit is cheap. But then you must make sure that your advertising has a high conversion rate compared to the old way of advertising. So the old way of advertising, maybe your conversion rate is 1 over 1,000. So 1,000 views, you get 1 conversion. But maybe the new way of targeted advertisement, even though it's more expensive, but then you publish only, you can get a ratio of maybe 1 every 100. So 100 advertising that you send to targeted customer with the right product, the one that they need, the one that can entice them, you can get 1 customer every 100 instead of 1 customer every 1,000. So there's a ratio of 10. So 10 last time was 50 cents. So the equivalent of 10 is 5 ringgit. So you can charge 5 ringgit per advertising instead of 50 cents. So you need to have that kind of measurable KPI so that you can measure how the project is doing. And then of course, if you have to be honest to each other lah. While you are developing the project, if something goes wrong, then you have to bring it up to the table already. That the machine is not learning as well as it is doing, and then let's look at certain way of correcting it, or you need to extend the time or whatever. These are things that you have to address during the development itself. Not today you have to send, today your machine is still not learning. It cannot be like that lah, basically.
Alright, thank you, sir.
Yes.
I got one second question. Is there any differences between the machine learning workflow between academics and industry? Is there any big difference like in their workflow? Like
Yes, definitely. So later in the slide, I will show you some workflows. That will be answered in some of the later slides.
Alright, thank you.
Yes.
That's all for me.
Very interesting questions. Any more questions? Come on, 1% of your mark is coming from here.
No, sir.
Okay, so we take a break now. Dr. Izam, how long do you want to take this break?
How about 5 minutes until we reach
The next prayer time.
Maghrib prayer?
Okay, can?
Yes.
Okay. So we take 5 minutes, then we come back at 6:30, right?
Yes, please.
Okay, guys. Okay, are we ready to restart? We will stop at 7:15 to break for our Maghrib prayers, right? We stop here. What are the components of neural network? Okay, let's look at the component neural network in a better way to understand them. TensorFlow has provided what is called a sandbox for us to try out the features of TensorFlow. Okay, we are going to visit the sandbox in a short while. So what I want to draw your attention to are the types of activation function, the normal types of activation function that is provided by the TensorFlow sandbox. You have the rectilinear function here. This is the rectilinear function. You have the tangent, hyperbolic tangent, which is this one. The one at the lower left, the one at the upper right is the rectilinear. You have the sigmoid function, which is the upper left. You have the linear function, which is the upper right. Okay, let me begin. And then what you have here is, you have, for example, how you want to divide the data between test data and training data. So how much data you want to use as a test data and how much data you want to use as a training data. Noise is where you want to introduce some disturbance in the data, some useless data. How big is the size, then you generate data over here. And then this is your neural network. You can see the neurons here. The input neurons are over here, and then in the middle there's a hidden layer. You can add a few hidden layers, and then finally you have your output neuron, which try to determine whether that particular dot is an orange dot or whether that particular dot is a blue dot. So what this neural network playground tries to do is it tries to draw a line to classify which dot are orange and which dot are blue. Okay, what we are going to look at is by changing these parameters that you have on the screen here, we try to improve the rate of learning of this particular model. This is just to give you a feel for how neural network works. And the exposure is the count, like how many times it goes through training in order for it to be able to learn. So I'm opening the playground here. Let's wait for a while while it's opening. Can you see my browser?
Yes, sir.
So the URL is playground.tensorflow.org, right? Okay. As you go in, you get the default neural network that TensorFlow provide. Now let's try to train this data using the default network. You see here there are blue dots and there are yellow dots. What they will try to do is they try to draw a boundary to define which area of the graph represents yellow dots, which area of the graph represents blue dots. And it's arranged in a circle like that. So we are now training. You can see it's going through a few times, sending data through to the neural network a few times. You can see the loss functions here going up. So this is where the loss function is being calculated, and you can see now it's coming out with some kind of a colored band over here. So it's guessing that the data is arranged in a vertical pillar. So any data that is in the middle represents blue dot. Any data that is on the left hand side or right hand side represents orange dot, which is actually not correct, right? Because the data is actually arranged in a circle rather than a pillar. So this is an example of the neural network not learning very well. It's still learning, it's still trying to refine. You can see that as the epoch is increasing, the number of times that it is training is increasing, but the graph is not changing. So that is like the saturation point in its learning process. It's not really learning so well. Okay. So we have divided the data, 50% training data and 50% test data. Okay. Maybe we need to add another. So we are using the hyperbolic tangent activation method over here. So now we have to think, how can we train our machine better? This is always a problem in neural network. How can we train the machine better? Maybe one of the way is we can add more hidden layers. So there's 4 neurons here, 2 neurons here. Maybe if we add more hidden layers, we can get some more. So let's add another layer, for example. Stop this one first. So now we have 3 layers. Okay, the first layer got 4 neurons, second layer got 2 neurons, third layer got 2 neurons. Maybe the middle layer we also increase by another 4. So we have 4 over here. All of this is using the hyperbolic tangent. So maybe in your architecture next time you are going to have some neurons are using hyperbolic. This layer, for example, using hyperbolic. This one using a different activation function. So what are the activation functions that we have? Later we'll go into all this in more detail. Here we have the linear rectifier. We have the hyperbolic tangent, sigmoid, and the linear. So this one later we'll do. So let's try now. Now we have changed this by adding another layer and also adding additional neuron in the other layer. We don't touch the other parameters yet. Let's try again whether it's able to learn better this way. You can see the loss function. What you want to do is you want to minimize the loss function. That's your aim. See, the loss function is reducing now, but there's still some inaccuracy involved because it's still thinking that this one is divided into pillars rather than divided into. You can see how they start to think. How every neuron is starting to reflect the thinking process. So if you do this kind of test, what you want to see is whether you are running more tests, but the solution has reached a saturation point. It is not improving at all. So if you see that it has flattened out this way, maybe it's not going to be learning a lot anymore. Just now it was very high, then it managed to lower, but then it reached a certain saturation point. It's not improving anymore. So maybe you should change the architecture into something else. maybe you also want to fit in this data inside them, for example. And see, the more data you fit in, what's going to happen? So now our input layer has 5 input values. Okay, we still haven't changed the activation function, and we still have so many layers. So let's try now whether it's working better or not. You can see now that the loss function is much more steeper. Now it's forming a circle already. Now it's much more accurate, right? So why is it more accurate? Because we changed the architecture of the network. We did not change the activation function or anything. You can see that it's already fairly accurate over here. This seems to be a good architecture for it to learn how to solve this problem. We haven't tried so many times. We have only trained it less than 50 times. It's already pretty accurate. Okay. Let's say we change the activation function to something maybe less accurate. No, let's try sigmoid first. Sigmoid is where you output from 0 to 1 instead of -1 to 1. Hyperbolic function is where you output from -1 to 1. Let's see how sigmoid works in this situation. Remember, this one is, you don't have -1, you have only 0 to 1. Not so very good. It's almost not learning anything. And if we start to use this rectilinear and or linear, I think it will be even worse. Let's take linear, for example. And try again. Linear is much faster. Less than how many? Less than 10 times. Already it's learning very fast. Okay? So those are the ways where you try to, a simple example of how you try to change parameters. We changed the parameter just now by changing the activation function. We also changed the design of the thing by adding another layer and adding certain other parameters or attributes to the input data. Right. Okay. So that is so our experiment here is over. I'll just stop this. You can see now is learning very fast using the linear function, activation function. Okay, linear is where, okay, so let's look at the various types of activation function. So the one that we saw just now was linear rectifier, sigmoid, and hyperbolic tangent. Now, linear is good because it can represent values that are more real world, okay? From negative whatever number to positive whatever number. So it's dealing with a broad range of, so what does the activation function does in the first place, okay? The x-axis is your input value, and the y-axis is your output value. So let's say, for example, this linear function, if you input 0, it will also output 0. You input 2, it will output 2. It can be 4, it can output 4. Or your linear can be much sharper. Instead of 2 output 2, maybe 2 output 4. 4 output 8. 6 output 12, for example. But it's still a linear. You can represent a lot of numbers. The problem with this is that you might be dealing with very large numbers if your situation is dealing with very large numbers. So that can have some implication in your calculation later on, because your number has no limit. Now, linear rectifier, this one here, you have a 0 value of output. That means if your input value is -10, you output 0. Input is -5, also you output 0. If your input is 0, you also output 0. But if your value increase to 5, you also output 5. What does this mean? This means ignore negative values. Okay, ignore those values that are negative and only start to react when the value is positive. Now, the 0 here might not need to be 0. It can also be, you know, ignore any number, let's say below 5. Below 5, don't do anything. After 5, then you start to do something. Or it can also be below 0, just output 2. But after 0, you start to output different values depending on the input. So straight line is mostly when the output needs to be real value. That means the value represents the real world instead of restricted to some range. So it's not restricted. It's as the number increase, you also increase, or the number decrease, you also decrease, something like that. Rectilinear is where just like linear, but when you need to only start to react, when you need to restrict output until a minimum input is reached. So you have some minimum value. After that, before that, you don't do anything. You disregard it. Only those that are above certain value, you start to react to it. Now, these two are compared to sigmoid and hyperbolic tangent. Sigmoid is an S-curve. It's shaped as an S, so this is also called an S-curve. How do you generate S-curve? You know that the formula for linear is y is equal to mx plus c, right? Y, your output value, is equal to your steepness or your slope, m, multiplied by your x value, plus certain constant. So certain constants can leave it above 0 or below 0. But sigmoid is different. Sigmoid, there's a few functions that you can use, including the one using the Euclid number. And basically what it means is that at the lower range of the input, you only increase the output very slowly. Okay? But in the middle of the range, you increase the output faster compared to the increase in input. So that's why the slope here is not so steep. This is the speed. So the slope here is not so steep. And then suddenly the conversion rate becomes very steep. So conversion rate, speed is also conversion rate. It's converting the distance that you are going through. So you are going much faster over here in the middle. But towards the end, you slow down. You slow down. And there is a maximum. The maximum here is 1. The minimum here is 0. Okay. So this slope, there is no straight line in the slope. It looks like a straight line, but there's actually no straight line in the slope. The speed is constantly changing. From slow to fast. This is the fastest point. And then you have slow until it slows down again. And the change is only restricted to between 0 and 1. The output is restricted to 0 and 1. So you take the input, which is somewhere in the middle. Let's say 2. 2 will produce an output of 0.5, for example. And by changing this formula or changing the parameters in the formula, you can have either a steep sigmoid or a shallow sigmoid, or you can have a sigmoid that moves to the left or moves to the right, or sigmoid that is move higher or move lower, or sigmoid that is longer or shorter or whatever. But those are basically, it's all sigmoid. Now, hyperbolic tangent is just like sigmoid. Sigmoid is the one in red color, restricting the value of output from 0 to 1. Now, hyperbolic tangent is different. It's restricting the value from negative 1 to 1. What's the value here of coming with a negative 1? Okay. You look at Spotify, for example. Spotify has a like button. Just like Facebook. Facebook has a like button. Spotify does not have a I don't like button. I don't like button. Spotify does not have. It only allow you to say I like or I don't. I zero. Zero can be I don't like or I am neutral. I don't care. It can be I don't like or I don't care. 1 can means I like. So you have the output of 0 to 1. But if you look at YouTube music, you also have a dislike button. So you can give a more precise input to your model. Because you can say now, 1 is I like, 0 is I don't care. Negative 1 means I don't like. If you don't like, then it also means that if you like, for example, rock music by certain artists, but you say, I don't like pop music by certain artists. So you are also learning, not only what the person like, but you're also learning what the person don't like. Let's say, for example, you know Led Zeppelin. Led Zeppelin sings Stairway to Heaven. And you know that people who like Stairway to Heaven will also like, for example, Scorpion. Scorpion will burn the sky, for example. So you know a lot of people who like this will like this. So next time somebody else come in and that somebody is somebody new and he say, I like Stairway to Heaven. So you know that he probably also like this particular music. Let's say Scorpion will burn the sky. But let's say, for example, you have additional information. The person who like this will like also Scorpion, but he will not like, for example, Lady Gaga. So you know 2 information now. He will like this and people who like this, normally they like that, but they don't like this. So you have a better prediction now compared to Spotify, which only knows what you like, but don't know what you don't like. Get what I mean? Hello? Everybody there?
Yes, sir.
Okay. Now, just now you saw sigmoid, right? You also have linear, rectilinear, which are linear, and you have the S-curve. Now, why do you use the S-curve? Which is sigmoid or the hyperbolic tangent. Here is the basic sigmoid function. You don't have to stick to one sigmoid function, okay? Using Euler's number.
Okay.
There are also a few other functions that you can use that will still produce a S-curve. But the character of the equation is different later when you come to the point of doing back propagation. The choice of function that you use can have some impact on the learning capability of your model. So you can see here on the lower left a few different S-curve. Why are the S-curve different? Because they are using different function. Okay, you can see the steepness of the curve, or the height of the curve, or the range of the curve is different when you use different function. Not only that, but you can also, in this basic sigmoid, normally what people put in front here is a constant. So it's not only sigmoid, but it's also a constant multiplied by sigmoid. So you can change that constant value. Or you can change this 1 into 10, for example. And then you have 10 plus Euler. So Euler number is one number. And then you can change some of these parameters. 1 multiplied by constant or something like that. And then you have an x value here. So you can play around with this. Play around with this so that you can change your S-curve. But it's still a S-curve. Only thing is it's changing. Okay. Because natural phenomena, a lot of natural phenomena actually follows the sigmoid. Let's say, for example, the pendulum. When you swing a pendulum, the pendulum is starting from the left. So as it goes down, the pendulum becomes faster. Here the pendulum is going very fast. And then the pendulum will climb back because it has momentum. It climb back. So it becomes slower as it climb back. And then it will stop there, and then it will reverse the swing. So in terms of speed, okay, you look at the green graph here. This is in terms of speed. It is slow, become faster. Right in the middle here, it is at the fastest. And then it becomes to slow down again. But it doesn't slow down in a linear fashion. It slows down in a curve. Slowly it becomes faster and slowly it becomes slower again. It's not immediately it's not straight away become fast, straight away become slow. So then it will become slow again like that. But you must remember that this fast and this speed is not the same. Because this one is going in one direction, this one is going in another direction. So the blue curve is taking the direction into account. This is going faster, but going up. And then now it's also changing direction. It's also now slowly, not really going up, but it's certain potential coming down, and then now it's down. Now it's down, then now it's at a different direction. And this one measures the speed. The red line here measures the change in speed. So as the thing goes faster, the change in speed is actually changing faster. But as the thing goes slower, it is slowly going slower. It's not going slower, it is slowly going slower. So that means there is too slow here. Slowly going slower. There are too slow. So one slow is the speed. The speed is becoming slower. Slowly going slower means it is slowly going slower. That means the rate of change in speed is also going slower. So that is represented by your sigmoid function. That means the rate of change of the speed. Okay, so that is why we normally use sigmoid function to represent data, the transformation of data, because sigmoid function normally observe natural phenomena. This is the pendulum. We can also think of other natural phenomena like the momentum a disease can spread. So normally a disease does not spread very fast. Disease will spread very slowly at first, suddenly it pick up speed. But as the community acquire herd immunity, it will slow down again. But it doesn't slow down immediately. It will also slowly become slow. It will slowly also change into slow. So you can apply it to the spread of epidemic, for example. You can apply it to the weight gain, weight loss. For example, when a person is young, the person is slowly becoming big. But during the teenage years, the person become very big very fast. And then once after a certain age, 30 years old, for example, the fellow stop growing anymore. But it doesn't stop immediately, not stop in one day. So slowly, it's slowly becoming slow again. So again, a sigmoid function. So you have the sigmoid function, you multiply by a certain number, then you can get maybe some estimate of the real world values. This is why you use the S-curve to do the activation function under certain circumstances. But as we saw just now when we did the playground, when you use the linear function, it's much better than to use the sigmoid function. So to answer your question, I'm sure you're thinking like, which one of these is the best for you to use? There is no very fast answer. You have to do a lot of experimentation, especially with phenomena that you're not familiar with. Like what we did just now was, we do experimentation. So this is also what you need to do experimentation. And you can see just now when we run the experiment for like 5 minutes, it has only run on my laptop using JavaScript. So it has only run 100 tests. So what if you need to do 10,000 tests, for example? If you use my laptop to do it, maybe you'll need like 15 days to finish 10,000 tests, and you cannot use the laptop for anything else. So this is where the question just now about transistors and about resources come into play. When you have to do a lot of parameters, you have to do millions of parameters, millions of calculation, you really need to talk about creating an efficient programming and also increasing your computing resources. Back to the slide just now where you saw there's a lot of lines in between the neurons. There is a lot of work being done over there. Okay? So we take a break here. We've overshot by 15 minutes, 7:30 now for Maghrib. So what time shall we reconvene? Dr. Izam?
We can resume at 8.
Okay.
Give him half an hour to get ready.
Okay. All right.
Okay.
Okay, guys. See you.
See you then.